3 was talking about the magnetic field of a bar magnet. So magnetism is a fundamental force of nature, and bar magnets are a common and straightforward way to study magnetic fields. A bar magnet generates a magnetic field that extends from its north pole to its south pole, creating a space around it where magnetic forces can be detected. In this experiment, the magnetic field surrounding a bar magnet will be investigated by mapping the magnetic field lines and determining the strength of the magnetic field at different points using a magnetometer on our smartphone. So the goals of this lab were to investigate the extent to which the magnetic field of a small bar magnet is dependent on its distance to a magnetometer, and to simulate the magnetic field of a bar magnet using a computational model in Python, and to compare the measured magnetic fields. So a preview of our findings: the magnitude of the net magnetic field increases as distance decreases. Our magnetic dipole moment of our bar magnet was roughly 3.1712 ammeters times meter squared. The measured off-axis magnetic field is about 0.0014 Tesla, and the simulated off-axis magnetic field is about 0.001017 Tesla. So some of the fundamental concepts we employed in this lab were the Biot-Savart law, the magnetic field of a dipole both parallel and perpendicular to the observation location, the magnetic field off-axis, and the magnetic field of a bar magnet. So this is a visual model of the magnetic field of a bar magnet. As you can see, the field points away from the North Pole towards the South Pole, while the dipole moment points towards the North Pole from the South Pole. And we set our system to be our observation point, which was our magnetometer or our phone, and the surroundings were the bar magnet, which was generating the magnetic field. So the procedure was, first we had to compensate for the magnetic north of the Earth, so we oriented our phone such that the magnetometer app had an x component of 0. Then we found the magnetometer chip on our phone. Then we measured the on-axis magnetic field by measuring the distance between the magnet and the magnetometer, where the magnetometer was along the dipole axis of the magnet. And we did this at 3 different magnetic field magnitudes, 20 Tesla, 70 Tesla, and 120 Tesla. And then we measured the off-axis magnetic field using the same experimental setup as for the on-axis. But this time we set the net magnetic field to be 100 Tesla. Then we recorded the Y component of the Earth's magnetic field, and then we moved our phone the same distance down the Y direction and measured the magnetic field at this location. So it was a vector distance 0 at a 45-degree axis, a 45-degree angle, as you can see here in the diagram. So the results of our data that we recorded in our spreadsheet. So here you can see the different recorded values for the magnetic field and the distance at different magnitudes of the magnetic field at the magnetometer. And then here you can see the off-axis field, different values for the magnetic field and the distance, depending on the distance. And then here's our regression line using a logarithmic relation where ln of bx equals ln k plus n times ln of r, where k is the slope of n is the slope of the regression line. And we can calculate k using this formula here. And then using this formula, we were able to calculate the magnetic dipole moment mu for the bar magnet. So the observations we found: when the magnetometer was far away from the magnet, it measured a near zero magnetic field in the x direction, as you can see here when it was further away here. And then as the magnetometer moved closer to the magnet, as the distance decreased, the measured x component of the magnetic field increased. As you can see, bx is greater as r is smaller. And then here's the computational model that we used in Python to be able to calculate the simulated magnetic field off-axis. So here we set our magnetic dipole moments, and then we use the off-axis magnetic field formula to calculate it to be 0.001 Tesla approximately at a 45-degree angle. And then the results, as I said, a 3.1712 amps times meter squared magnetic dipole moment. And then here are our experimental and our simulated off-axis magnetic field. They varied by about 40% error, and we think some sources of error were nearby magnetic fields, like from our light post, from like some other smartphones or other devices. And we were also near the library, which had a lot of wires that could have generated a magnetic field. Also, the inconsistent placement of the phone during measurements, so like we could have moved it around slightly and not accounted for that. Just like errors when reading the measurement on the magnetometer, and the surface on which we measured it was not completely flat, which would have changed the z component to not be 0, which could have affected like our experimental value of b. So what if we hadn't oriented our experiment to compensate for magnetic north and had instead laid out our meter stick at some intermediate angle with respect to Earth's magnetic field? So the magnetic fields would be different due to not accounting for the magnetic north. So both the x and y components would be different if it was at an intermediate angle, because the magnetic field measurements would not account for the magnetic north, so it would be like added to it. Because we laid the magnetometer on a flat surface, the z component would not change, or we would see negligible changes. And if we were to stick 2 identical magnets together end to end, the magnitude of the magnetic field would increase due to the superposition of the magnetic fields from the 2 magnets. So it would be like twice the magnitude. And the measured distances between the magnets would decrease due to the increased magnetic field magnitude from the 2 magnets. Thank you.